Now, I would like to go a little bit deeper into the understanding of the discrete time signals and introduce some additional definitions. Okay, so some definitions which are pertaining to the discrete time sequences. We have a discrete time sequence represented by x of n. There is a sequence, we represent it in terms of a sequence of numbers. We say that this sequence can be either a finite length sequence or it can be an infinite length sequence. Infinite length sequence. Okay. Now, when do we call it as a finite length? A finite length sequence means it has a starting index where it becomes non-zero and then ending index where till where it is non-zero. After the outside of that, it is a its value is equal to 0. So, a finite length sequence x of n is non-zero in a range n greater than or equal to n1 less than or equal to n2. Okay. And how do we define n1 and n2? n1 must not be minus infinity. So, it must be some number that is greater than minus infinity. So, minus 10, minus 12. So, n1 cannot be, it's not equal to, it is greater than minus infinity. Similarly, n2, the upper limit must be less than infinity. It cannot go all the way to infinity. Neither end can go to infinity. Under this condition, you will get a finite length sequence. Okay. So, unit step, clearly it is a finite length sequence. Yes? No. This is not finite length. It is a infinite length because it starts at n equal to 0 but then goes all the way to infinity. So, this is a infinite length sequence. The unit sample function is a finite length sequence, belongs to finite. So, I guess you now are you now have a way to visualize what a unit step, a finite length sequences and infinite length sequences. Now, the length of a finite length sequence, how many non-zero samples do you have? Length of a finite length sequence. You classify it as finite length, then you are representing it. So, finite length sequence. Let me give it to you in the form of an example first. Supposing the non-zero values are corresponding to the values of n minus 2, minus 1, 0, 1, 2, 3. Okay, these are the non-zero values. These are the points at which you have non-zero. So, count them. This is 1, 2, 3, 4, 5, 6. Length equal to 6. Okay. Now, what is the starting value? n1. Ending value is n2. Okay. And the length of the sequence is always defined as n2 minus n1 plus 1. n2 minus n1 plus 1. Did we get that correct? n2 equal to 3, n1 equal to minus 2. So, 3 minus of minus 2 plus 1 should be equal to 6. So, this is the value of the length of the sequence. Okay. Now, let me give you an example. Supposing I told you I have a sequence that is non-zero in the range 2 to 5. Okay, this is easy enough. You can count and see how many non-zero values you get. Obviously, the length of the sequence, length uppercase n is equal to 5 minus 2 is 3 plus 1 equal to 4. You can easily calculate. But if it's some large value, negative numbers, it doesn't matter. You can always apply this formula. The length equal to your right side, right hand limit minus the left hand limit plus 1. Always that is the formula. Okay, so use this as a way of representing the signals. Now, there is a very important classification of signals which are known as causal or non-causal signals. So, classification of a causal signal. You have to be very, very precise and careful in applying the definitions that we are talking about. A causal signal x of n can be classified as a causal signal if x of n equal to 0 for all negative values of n. Okay, it has to be equal to 0. It's not. It can be 0 on the right side also. But the important thing is n less than 0, there should not be even a single non-zero value. Then it qualifies as a causal signal. Okay, unit step, u of n, causal signal. Yes, it has one. Basically, it is non-zero only in the positive indices. Correct? Okay, this starting at n equal to 0 and then it's 0 everywhere. So, this would qualify as a causal signal. On the other hand, if I defined a signal x of n equal to u of n plus 1, advanced, shifted sequence, what does x of n look like? X of n looks like there is 1 at minus 1, there is 0, then 1, okay, this is 0, 1, 2. Now, you cannot make the argument, see, if u of n is, you call that causal, why not call x of n as causal? The answer is no. Why? Because there is a non-zero index for which you have a non-zero value. So, x of n is not a causal signal. So, you can qualify by doing a simple test. You can say, is it causal or not? Don't use the word non-causal because non-causal has a different definition. And so, this is the important definition. So, causal signals belong to a family of signals which are called right-sided signals or right-sided sequences. What do we mean by right-sided sequences? It starts at some value of n and then is non-zero towards the right. So, basically anything to the left of it is 0. So, a right-sided sequence, all causal sequences are right-sided sequences. X of n must be equal to 0 for n less than n1. Notice that n1 can be positive or negative, okay, and n can be infinite length also. Basically, this is a sequence that can be of infinite length, can be infinite. So, right-sided signal. So, for example, is unit step a right-sided sequence? Yes. What is the value of n1? n1 is 0. So, can be infinite length sequence. Okay. Is x of n a right-sided sequence? It was not a causal sequence, but is it a right-sided sequence? By looking at the definition, if you take n1 equal to minus 1, anything to the left of it is 0, anything to the right of it is equal to 1. So, x of n is not a causal sequence, but satisfies the property or definition of a right-sided sequence. So, I hope you are comfortable with it. A causal signal, a right-sided signal, and a causal signal is a subset of a right-sided signal where the origin is at n equal to 0. Right-sided signal can be, like we showed, minus 1, minus 2. Anything to the right is non-zero, anything to the left is 0. Okay. Now, opposite of a causal signal is anti-causal signal. Anti-causal signal. Okay. Now, again, definitions very, very important. And x of n is an anti-causal signal if x of n is equal to 0 for n greater than or equal to 0. Okay, n greater than or equal to 0. And it again, this can be infinite length, can be infinite length. So, let me ask you, give you a simple example of a anti-causal signal. Okay. Now, u of n, you know the definition, unit step. Now, if I tell you that x of n is equal to u of minus n, that means it's a time reverse signal. Can you sketch it for me? So, u of minus n will say is non-zero at n equal to 0, n equal to minus 1, minus 2 and so on, and it will be equal to 0 for all these values. Okay, so this is 0, 1, 2, 3, minus 1, minus 2. Okay, this is u of minus n. Does this satisfy the condition for an anti-causal signal? The answer is no. Why? Because your signal, for an anti-causal signal, must be equal to 0 for 0 and all other indices greater than 0. So, this does not qualify. So, x of n, which is u of minus n, is not an anti-causal signal. Anti-causal signal. Okay. Okay. On the other hand, what is u of n minus 1? U of n minus 1 is a shifted version. So, it is 0 everywhere, it 0 at n equal to 0, and starting from 1 it will be, this will be, so this will be equal to 1. Okay, there is a 0 here. This is u of n minus 1. So, if I define y of n as u of, so let us say that this is x of n is u of x of n is equal to u of n minus 1, and y of n is equal to x of minus n. Okay, you can easily verify this is nothing but u of minus n minus 1. What will that look like? It's basically a mirror image of u of n minus 1, and it will look like this. Okay, starting from minus 1, it will be minus 1, minus 2, minus 3. This is 0, 0, 0, 0, all these values. Okay, now this will satisfy the property of a anti-causal signal. Anti-causal signal. Okay, so anti-causal. So, definition of a causal signal, definition of an anti-causal signal, I want you to be very, very careful, very be able to apply. Just like we defined a right-sided sequence, we can also define a left-sided sequence. Left-sided sequence. A left-sided sequence is a sequence x of n which is non-zero beyond a point on towards the right. So, basically it is non-zero on the left side, and it's 0 on the right side. So, if x of n equal to 0 for all integer values n greater than n2, okay, where n2 can be positive or negative, does not matter. There is a point beyond which it is all zeros. Such a sequence is called a left-sided sequence. Okay, and is an anti-causal sequence a left-sided sequence? Anti-causal sequence is a left-sided sequence. Okay, and basically you can substitute and see, you get n2 equal to 0, therefore basically you will see that all points are to the right side of it. So, anti-causal sequence is also a left-sided sequence. So, basically again, just like right-sided sequence is a superset, left-sided sequence is a superset. Now, is u of minus n a left-sided sequence? U of minus n is a left-sided sequence, left-sided, okay. U of minus n minus 1, but okay, but not anti-causal, not anti-causal. On the other hand, u of minus n minus 1 is a left-sided sequence, and it is also anti-causal. It satisfies the properties. So, you should always write down the definitions very, very carefully, so that there is no confusion in your mind as far as the basic definitions that we are referring to. Okay, I hope you are comfortable with the points that we have mentioned, and you are able to apply these definitions in a very careful and precise manner. Now, what I would like to do is to introduce for you a very important difference between the behavior of the sinusoids in discrete time versus continuous time. Remember, I told you what that the sinusoids between continuous time and discrete time, there are some very significant differences, though they look similar in terms of their, the way, the oscillatory nature, all of that, but something very, very important that you should be aware of in the context of the. So, let us look at the properties of the discrete time sinusoids.